Hello everyone, thanks for coming. Today we're going to do a review of our week 5's lecture for linear algebra. So in this week, we introduce 4 fundamental subspaces associated with matrices as well as linear transformations associated with matrices. So there are 4 fundamental subspaces determined by a matrix. The column space, space spanned by the columns, null space, the solution to Ax equals to 0. Then if we transpose A to A transpose, then we have the row space as a left null space. So the null space and the column space of A transpose belong to Rn, while the column space as a null space of A transpose belongs to Rm when A is an m by m matrix. All 4 subspaces are governed by the rank R, the number of pivots. So the dimension of the column space and row space is R, while the dimension for the null space is m minus R, and the dimension for the left null space is m minus R. The dimension of the column space plus the dimension of the null space is n, while the dimension of the row space plus the dimension of the left null space is m. So those are the key properties of the 4 subspaces. So how can we determine the row space and the column space as well as the null space? So we will need to find bases. Well, Gauss elimination, the row space is it consists of the non-zero rows of echelon form of U. They will form a basis for the row space. The null space, however, can be constructed by using the special solutions. Basically, for the free variables obtained using the Gauss elimination, we set one free variable to be 1 at a time. We get a series of special solutions, and those solutions will form a basis. For the column space, the pivot columns of the echelon form U identify the basis columns in the original matrix A. The key property is that the row rank equals to the column rank for the matrix. Also, the null space is orthogonal to the row space, while the left null space is orthogonal to the column space. Specifically, if we have a square matrix and the matrix has full rank, then the matrix is invertible and both null spaces contain only the 0 vector, the null space as the left null space. So for a general n by n rectangular matrix, we can also talk about the pseudo inverse. If the matrix has full row rank, then Ax equals to b is solvable for array B. This guarantees the existence of solution. If the matrix has full column rank, which means that the matrix is very tall and thin, then the solution is unique. Rectangular matrices cannot have both properties if m does not equal to n. However, if m equals to n, then existence is equivalent to uniqueness of the solution. So if the matrix has full row rank, then we say that the matrix could have a right inverse. If the matrix has full column rank, then the matrix has a left inverse. So for the square matrix, the left inverse exists only when the right inverse exists, and invertibility occurs exactly when the matrix has full rank. For the one-sided inverse, the left inverse can be given by this formula, and the right inverse can be given by this formula. So note that the left inverse and right inverse, they may not be unique. The left inverse exists when the matrix has full column rank, while the right inverse exists when the matrix has full row rank. Another special case is the rank 1 matrices. The rank 1 matrices is the smallest non-zero, has the smallest non-zero rank, and the rank 1 matrix can always be written as the outer product form, basically the product of a column vector and a row vector. columns are multiples of U and rows are multiples of another, the transpose of V. So there is exactly one pivot for the rank 1 matrix. Basically, rank measures the number of independent rows and columns. Full rank controls the existence and uniqueness for square matrices, and the rank 1 matrices serve as building blocks, basic building blocks in linear algebra, because we can obtain more complicated matrices using those rank 1 matrices. Finally, matrix multiplication for matrix and vectors defines the linear transformation. Linear transformation preserves linearity. T cx plus dy equals to ctx plus dty. And linear transformations can act between different spaces. So this is done by using rectangular matrices. The concept of linearity actually applies to any vector space, not just the Euclidean space, like the space of polynomials, matrices, and functions. Linear transformation can be completely determined by its action on a basis of a space. Therefore, every linear transformation can be represented by a matrix, although the matrix can be infinite dimensional once bases are chosen. Matrices and linear transformations, they are two equivalent ways to describe the same linear action from one space to another space, linear space. Thanks for listening.